Hi everyone. Today let's talk about sessions 4.5, linear approximations and differentials. Big idea. If you look at a small enough region of a function near a given point, the function can be approximated pretty well by its tangent line at that point. Big skills, you should be able to approximate a function's value without a calculator. Or you just use simple addition, subtraction, multiplication, and division. No other like fancy function like square roots, exponential, and logarithm. Okay? So we will use the tangent line at a point as an approximation to the curve where x is near a. Okay, so we look at this picture. You can see here this is a. This is f of a. Alright, if we zoom in, okay, can you see this region? Do you see the functions behave very similar to the tangent line? So that's why when x, let's say x is here. So when x is closer to a, well, this is f of x, that is Ln of x. So f of x and can be approximated by L of x. So L of x is the tangent line. Okay. So we will use tangent line as approximation to the curve near A. So the Poinsot form of the tangent line at the point A is f of a plus f prime of m minus a. Well, if you can remember, the Poinsot form was y minus y of a. That's the y coordinate of that point, equals to the slope times x minus a. So we both sides plot. So y of a is the same as f of a. So we both sides add f of a, so we get this guy. So this is our linear approximation, okay? So linear approximation, L of x, linear because it's a tangent line. In Calculus 2, when we learn like chapter 9, we'll talk about Taylor polynomial, then we can have higher order approximation. But right now, let's just talk about linear approximation, using the tangent line to approximate the function. Okay. So how do we work on this example? Alright, let's see example 1. Use linear approximation to estimate the value of square root of 1.1. So assume now we can only use the basic operation. Plus, minus, multiply, and divide. So square roots we don't know how to calculate, right? So we're going to use the linear approximation to estimate the value. So what is the first step? Well, the first step is define my function. So here you can see square roots. So let's define our function to be square root of x. Okay? And we also need to figure out what is a. So a is some points that we're easy to find f of a and f prime of a. So a is, let me draw it here. So a is a good number that is close to our number 1.1. Okay? What's good number means? Well, good number is good number means you can find f of a and f prime of a easily. Okay? So you can find f of a and f prime of a easily. For example, if you have square root of 15, what's your a? Well, what is a good number that close to 15 such that you know the square root of that number? Well, that's 16, right? Because you know square root of 16 is 4, so we know it. How about cube root of 30? Well, what's your a? Well, Key roots. I know key root of 27 is 3, so A is 27. So A is some number that is close to our target points, okay? Such that we know f of A and f prime of A easily. Okay, so here, even though like 27 is not like as close as 30, such as like 29 or 28 or 31, but we only know like cube roots of 27 without a calculator. So the good number is 27. How about 66 square roots? Well, that is what? 64, because you know the square root of 64 is 8. So 64 is a good number. Okay? So here, what is the good number? A good number close to 1.1, such that you know the square root of that number is 1, right? So let's continue. So A is 1. And then what is f of A? Well, f of A is f of 1, which is square root of 1, which is 1. See? We can find f of A easily without a calculator. Okay, next, let's differentiate. So f of x equals to square root of x. That's the same as x to the 1/2. So when we differentiate, we get 1/2. X to the minus 1/2. So far, so good, everybody. And we also need to figure out f prime of A. Okay, so A is 1. We plug in 1 in it. But 1 to the whatever is 1. So the answer is 1/2. That's the second step. The third step, we can then write down our tangent line equation. So this is also our linear approximation. So that is f of A plus f prime of A times x minus A. So have this formula in mind. F of A is 1. F prime of A is 1/2. We have x minus A. What is A? 1. Okay, so this is our tangent line equation. So just keep it like that. You don't need to simplify. Okay, you will see why. So the next step, square root of 1.1. This is like f of 1.1. Okay, so because f is square root of x, so you're like putting in x equals to 1.1. So that's approximately equals to L of 1.1. What is that? Well, you plug in 1.1 into our tangent line equation. So 1 plus 1/2, 1.1 minus 1. See? 1.1 minus 1 is 0.1. So 1/2 times 0.1 is 0.05. So the answer is 1.05. Okay, so a typical mistake is sometimes students plug in square roots of 1.1. So let me put the typical mistake. The typical mistake is sometimes students put square root of 1.1 here. No, you don't want to plug in square root of 1.1. Think about it. What are we doing? We're doing all of this because we don't know what is square root of 1.1. But if you can put square root of 1.1, then you don't need this linear approximation if you know how to calculate the square root of 1.1. Okay? So when you plug in, this is only the x values. It's the things inside the square roots. Okay? And we can also check our work. So for the problems in this session, it's very great because you know whether you're doing right or wrong. So you can check our value. Square root of 1.1. You put this in your calculator. Okay? What do you get? Let me plug in square root of 1.1. So I get 1.0488088848. Are they close? Yes, they're close, so we're doing right. Okay, so for problems in this session, you kind of have a feeling of whether you're right or wrong. Okay, so those are the 4 steps. First, we define the function f, and then find the good number a, and evaluate f of a. Second step, we differentiate the function, and then we plug in a to find f prime of a, that is the slope of our tangent line. And then 3, we know the slope, we know the y value, we can write down the tangent line equation. Okay, and step 4, we can then estimate our value and make sure figure out what is the x. Okay, and then you're gonna put that x values into our tangent line equation. Okay, and then step 5, you can check your work. So see whether they're close. If they're not close, maybe something wrong, go back and check your work. Maybe you differentiated wrong. Okay, let's continue to look at example 2. Use the linear approximation to estimate the value of sine of 2.5 degree. Okay, so let me use black. First steps, define our function. What is that? I really hope that you can pause the video and try to work on this problem first. Are you done? Let's check our answer. So f of x is sine of x. Okay? And what is the good number? Well, what is the good number? Do you put like 2 degree or 3 degree? No, neither. Okay, so let's come back and look at our what's 2.5 degree? 2.5 degree, let's change to radian. So how do we change to radian? Let's see. Pi has how many degree? Pi has 180 degree, right? So degrees cancel. And 2.5 over 180 is actually pi over 72. So this is radian. Okay, so change to radian. What are the special angle? Well, the special angle angles are 0, pi over 6, pi over 4, pi over 3, and pi over 2. Those are the special angle, right? Pi over 72. Which one is closest to it? I would say 0 is the closest. Do you agree? If we change to the degrees, so the special angles are 0, 30 degree, 45 degree, 60 degree, and 90 degree, and 2.5 is closest to the 0 degree. Okay, so A is not that. So A is actually 0. Okay, then let's continue. F of A is then sine of 0. That is 0. That is the first step. So far, so good, everybody? Second step, we want to compute the derivative. So the derivative of sine x is cosine x. And what is f prime of a? So that's cosine 0. What's cosine 0? 1. Alright, so what is our linear approximation? We have the f of a, which is 0, plus f prime of a, which is 1, times x minus a. A is 0. Oops. So that is just x. So our linear approximation is just x. Okay, and then 4, we have sine of 2.5 degree. That is sine of pi over 72. This is why you must change the degree to radian. Because x, well, when you talk about x, that's length. The length, you have to use radian. So that's approximately L of our x is pi over 72 radian. So that equals to x. So x is pi over 72. Okay, so we can also check our answer. So let's see if you, let's check. Okay. So if you plug in a calculator, pi over 72 is approximately 0.0436333231. Okay, and we also want to check sine of 2.5 degree. So by the calculator, that is sine of 2.5. So when you plug in it, make sure you're in the degree mode. Okay, and I get 0.0436193887. Are they close? Yes. If they're close, that means we're doing right. Okay, so that is use the linear approximation to estimate the value. Okay. Let's go to the next topic. Okay, if y equals to f of x, where f is a differentiable function, then the differential dx is an independent variable. The differential dy is then defined in terms of dx by the equation. Well, do you remember we know dy dx is f prime of x? That's the derivative. You can kind of treat it like we multiply by dx on both sides. If we multiply by dx on both sides, what happened? So it's like, oh, I get dx here, I get dx here, they cancel. So I get dy equals f prime of x dx. So this is the differential form, okay? And you can think that our independent variables are x and dx. So these are independent variables. Okay, and the dy is a dependent variable. Okay, so this is dy is like a function of two variables, the x and the dx. Okay, so if we let p, which is x, f of x, so this is point p, x, f of x, and q, so let's say this is the q, x plus change of x, so we know this guy is change of x, so x plus change of x is right here. So q is x plus change of x, and this is f of x plus change of x. That's the point q. So p and q are both on f, okay? And we let dx be change of x. Then what is the corresponding change in y? Well, the change in y is the change of the y coordinates, right? Which is f of x plus change of x minus f of x. Okay, now what is dy? Well, dy is, okay, because we know dy is f prime of x dx. So that's why we get a linear function, okay? So this is dy, and you can see dy when change of x is getting close to 0. dy and change of y are very similar. Oops, there is a typo. Okay, so when change of x getting close to 0, change of y is approximately by dy. dy is f prime of x dx. But because here we're letting dx be change of x. Okay. So this is our formula. We have change of y approximately f prime of x times change of x. Okay. So use this formula to solve the following problems. Part A. Approximate the change in y equals to f of x equals to x to the 9th minus 2x plus 1, where x changes from 1 to 1.05. Okay, so how do we do that? Well, first, you gotta figure out what's f prime, right? So f prime of x is 9x to the 8th minus 2, right? And we're looking for x changes from 1 to 1.05. So over this region, what is a good number? Okay, so over this region, the good number is 1. Okay, so you pick it. Remember, you pick the good number that is easy to calculate, and which is within this region. Okay, I can give you maybe minus. I can give you maybe 0.89 to 1.02. Well, the good number is also 1. Okay, for example. Okay, so a good number that is a number is easier to calculate and it lies within the region. Okay. So the second step, f prime of our good number. Oops. Okay. All right. So we plug in 1, we get 9 minus 2. Well, that is 7. Right, everybody? So that is 7. And what is change of x? So next, change of x is we use the final value 1.05 minus the initial value 1, so it is 0.05. Finally, change of y is approximately change f prime of 1 times change of x. F prime of 1 is 7. Change of x is 0.05. So we get 0.35. Because it's positive, we say y increases by approximately 0.35. Okay, so that's how we answer it. So far, so good, everybody? Okay, let's go to part B. Approximate the change in the surface area of a spherical hot air balloon when the radius decreases from 4 to 3.9 meters. Okay, so surface area. Do you know the surface area of a sphere? Oh, surface area is 4 pi r squared. That is the surface area. Okay, so we want to figure out what's s prime. S prime, 4 pi, stay there. Derivative of r squared is 2r. So we have 8 pi r. Okay, what is a good number? Well, a good number between 4 and 3.9 is 4. Okay, so A is 4. So second step, we plug in s prime of 4. That gives us 8 pi times 4. That is, what is 8 times 4? 32 pi. Great. And then let's continue. Change of r. We use the final value minus the initial value. We get negative, and it makes sense because it's decreasing, right? And finally, change of surface area is approximately s prime of 4 times change of r. So it's 32 pi times negative 0.1. So it's negative 3.2 pi. Okay, so you can put this in your calculator. That's approximately negative 10.05. So we can answer a problem like the surface area decreases by approximately 10.05. Okay, so here you gotta be careful. Because you say decreases by 10.05. If you put a negative here, it means you decrease negative, it means you're actually increasing. So when you say decreases, you don't need to put a minus sign here. So when you say decrease, don't put a minus sign here. Because if you decrease a negative number, it means it's actually increasing. To negative, make it positive. Okay, so that is part B. How about part C? Okay, so try this problem, everybody. So what is the first step? The first step, we want to take the derivative. Well, what's the derivative? This is like chain rule, right? We have 3 cosine x squared. So chain rule. Derivative of 3u squared is 6u times u prime. What is the derivative of cosine x? Well, that's minus x, right? So we have minus cosine, minus 6 cosine x sine x. And here, because we don't know how the x is changing, so we can then just use our formula, approximate change. So change of y is approximately f prime of x times, because we're given a small change dx, so let's keep it dx. So that's negative 6 cosine x sine x dx. Okay, so this is our answer. So far, so good, everybody? So that is the linear approximation. Bye.